Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing mathematical modeling. Chapter 2 is going to be discrete time models. Specifically, section 2.1 is going to be introduction and examples. This lecture, what we're going to do is we're going to start with some motivating examples to see how to analyze discrete time models, and in particular, what a difference equation is and their classifications. Let's get to it. Okay, this chapter deals with models with a fixed time interval between measurements of the quantities involved. There may be more than one quantity. We'll get more and more complicated as we go, but for now, when we teach this, we're going to talk about one quantity, x usually, to keep the notation consistent. So if we have a variable x in the model, what we're going to do is, to do this discretely, we're going to view, in the example we're going to do right away, it's going to be every 30 minutes we're going to do a measurement of something. But at the time interval, the length doesn't matter, but we fix a specific time interval, and then we only make measurements about the quantities in the model at those fixed time intervals. This is going to give us a discrete model, and what this is going to do is give us a sequence of numbers, x0, x1, x2, xt. This is the classic notation for a sequence of numbers. And what is that representing? Each of these xt's is representing the quantity of the variable x at the time t. And then we'll get one for every time as we go in measurements in this experiment. What we're also assuming is, in some way, shape, or form, and this is how we're going to phrase difference equations as recurrence relations. What we mean by that is the quantity xt plus 1 depends somehow on the previous states xt to x0. Again, at first what we're going to do is assume that xt plus 1 depends only on xt, and then we'll do a little bit where it depends on a couple of them. Fibonacci sequence, and those ones need a couple of these guys. But right now, to motivate how we're going to get the definition of a difference equation, let's look at a specific example of bacterial growth. All right, for our first example, we're going to look at bacteria growth in a nutrient solution at a fixed temperature. Don't worry about all the sciencey type of things. We're just going to worry about how do we analyze this. This is some actual data from a specific bacteria that I guess I stole from somebody else, but I just want to use the data specifically for, we didn't make it up. You could make it up, but you would see the same thing. But since I have the real data points anyways, let's use them and see how we have a bacteria growing. What we're doing is we're looking at the density of that bacteria, regardless of how they measure it and what the units are. It doesn't really matter, but this is the density, they're saying, in some units of what they get for that biomass of the bacteria. These are the timestamps, and specifically in this one, what they're doing is they're looking at, they give the time when they recorded these values in every half an hour, so every 30 minutes or every 0.5 of an hour. That column actually is not important for us. It can be deleted from the scenario. It's just what has been given. Once they fix the unit time, half an hour or 30 minutes, we have time 0, time 1, time 2, and we're just going to record them as each timestamp. So what I've done now is plotted with our times from 0 to 6. I've now plotted those densities. We're going to call, in this model, we're going to call the density of the bacteria xt, or the variable x will be the density of the bacteria at any given time. Because we're using discrete, it'll be xt. Then I plot this, and we see that we have an increasing function, so the bacteria seems to be growing over time. We want to know, how do we model the growth of this bacteria over time? What we're going to do is we're going to assume that, for simplicity, in the first one we can do this and get more complicated models, but for this one we're going to do is we're going to assume that xt plus 1 is a function of those previous terms somehow, but for simplicity we're going to assume that it just depends on the last state, xt. And now we want to know, what is that function? Often, which is the case here, to find out what that function is, you want to analyze xt plus 1 minus xt. This is why they're called difference equations, because you can derive a lot of the time what that function is going to be from their difference, or sometimes from their ratio, and you can't tell, so I've listed both. It seems like in this one, in this scenario from the model that we've got, which is bacteria growth, I don't know what was in quotes, it actually is bacterial growth, but in this one it seems like the difference between them is increasing. It keeps getting bigger, the value keeps getting bigger, just like it shows here. It's an increasing function when we plot them. But the ratio of xt plus 1 over xt, the ratio of those populations, or the density at each timestamp, seem to be, and again, this is with, you have to look at this with the scientific eyes. We're trying to find a pattern, and the first two are outliers, or maybe the growth rate isn't quite constant. Maybe it's slightly faster at the beginning, but once it gets a few, if I look here, 1.56, this one dipped a little bit, but these start helping me see a pattern. And if I didn't, I would take more and more recordings of the bacteria over more and more hours, and I would see that 1.56, 1.59, 1.58, it looks awfully close to a constant value of 1.6. So what we're going to do is we notice that xt plus 1 over xt is approximately equal to 1.6. So that's going to be our assumption. We're going to assume that xt plus 1 over xt is equal to some constant value r, some rate, growth rate. What we're going to get from that immediately is that xt plus 1 is actually equal to rxt. And that says, what is the function? F of x is rx. We've now found an idea of what we think, how to produce the next generation from the previous generation of this bacteria density. Then, because we notice also from the actual data that this is 1.6 roughly, what we can do is if we look at xt plus 1 equals, let's do 1 decimal point above and 1 decimal point below. So we'll get 1.7 xt, say, and then let's try to model with x plus t equals 1.5 xt and see how accurate that gets us. This is the actual data. Now let's use the magic of editing and plot a bunch of values for what we would get here. Right now this is the xt, this is x0, specifically x1, x2, x3, x4, x5, and x6. This is the actual experimental data for those densities. Now let's assume in our model that we're assuming that this is the actual growth rate and see how close or accurate we get to our model's values to the actual empirical experimental data. Using model 1, we're going to call it, and model 2, with model 1 is using 1.7 as the growth rate, constant growth rate, and model 2 is using 1.5. We used the relationship that we thought we had, which was what? Xt plus 1 equals r times xt. If we assume that that's our function, we put a couple r as 1.7 and r as 1.5 in there. I use this to calculate all the generations, so you didn't need to see that. Then what we do is plot, and we see that this is model 1 and this is model 2, and we can see that by doing 1.7 it got us fairly close, and by doing 1.5 it moved us further away, so that we are pretty sure that this is A. What this tells us is this is the actual data, and then these are our models based on, and then trying to parameter fit or tweak what that parameter is. And it shows us that regardless of the value we picked, as long as it's fairly close to 1.6, it seems like it's an underestimate for the most part. This one finally tipped over, but we're fairly close to getting an accurate value of each generation's population density based on our models in comparison to the real world data. So this is the idea. And of course, what we're going to do in general is try to model these things with recurrence relations, or what we're going to call difference equations, the terminology coming from. We can set everything up in this form for simplicity, and to relate them to recurrence relations, we're going to put them in a slightly different form. Let's give the general definition of a difference equation. All right, from example 1, we get the idea of what we want to call a general difference equation. In short, a general difference equation is a rule or a function which instructs how to compute the variable in time period t plus 1 given the current and past values of that variable and time. We need to know the information about the timestamps. But what that does for us is gives us, and usually we work backwards, so I'm going to try and give us the specific cases of these horrible equations which we're going to focus on. But the most general scenario, what they're saying is we can write this, we can move everything to the left hand side classically and write it as equals 0. But what this is saying is xt plus 1 and there all the other previous timestamps and possibly the variable t are all some function which describes how that system works, that we call non-autonomous if the function actually explicitly involves t. We may have many scenarios where we don't have to use t. These are actually easier to solve, and we're going to call that non-autonomous, or homogeneous and non-homogeneous respectively when we view them as recurrence relations. So this is the most general horrible one. These would include nonlinear, or when I can't separate this xt plus 1 explicitly. You maybe can't see this yet. We'll do some examples and show you what I mean by this, but we're always going to assume in the ones just like the last one we did that we can solve uniquely for the highest timestamp. So xt plus 1 we can always solve uniquely, which means either it's linear in that variable so we can just solve for it, or it's some invertible function so we can get rid of it. If it was xt plus 1 cubed, we could take the cube root of everything else and we can uniquely solve for that guy. So we're always going to assume that. Therefore, this is the most standard form that we're going to use in the course, and this is where I'll always start from, is assuming xt plus 1 is some function of the previous states and possibly time. Again, if time is involved, we're going to call this non-homogeneous, and if time is gone, we will call this homogeneous. Let's do one more remark and then we'll get into, in the last scene of this video, basically what we're going to do is point out, that's great, now we know finally how to set up, in a lot of cases, these difference equations. What does it mean to get a solution to these, and how do we analytically go about solving linear or non-linear, homogeneous or non-homogeneous recurrence relations or difference equations? Let's get to it. Remark 1 before we end this video. The term difference equation comes from this notation. A lot of the time what we're going to say is the difference between those two generations. I think about populations all the time, so I use the terminology generation. But in the bacteria growth, generation T or generation T plus 1, the difference between timestamp T plus 1 and timestamp T is going to be some function of the previous states and possibly time as well. So this is why we get this obvious difference equation terminology. But a lot of the books, and including us and the book that we're using, and what I'm going to do is we're going to write the difference equation like this. And then you're like, you keep calling this a difference equation, but I don't see a difference anywhere. Where did you get the terminology? Because what we're going to do is basically just bring this guy to the other side. Now we've solved uniquely for t plus 1. That's the assumption we just made. But if I do that and bring him over and call this guy f as just xt plus this other guy g, we can write this as xt plus 1 solved uniquely as a function of the lower timestamps. Classically, this is going to be where we start with and what we call a difference equation, but it really comes from this notation. The last thing we're going to discuss is the order of a difference equation. So difference is being used in a different context. Given a difference equation, this guy, the order of that is the difference between the largest and smallest time index. So this is the largest time index, t plus 1, and this is the smallest time index, t0. As a couple quick examples, if I have this one is actually, you'll see in the next videos, this is how we set up the recurrence relation or the difference equation for the number of moves to solve the Tower of Hanoi. And this is the classic one. This is how you breed rabbits or bees and stuff like this. This is going to be the Fibonacci numbers, or Fibonacci sequence, or Fibonacci difference equation now. So this one is t plus 1 minus t is equal to 1. So the order is 1. This is order 1. In this one, I have t plus 1 as my largest index, and my smallest index is minus t minus 1, which is going to be give me cancel, cancel, and then these add to give me 2. So the order is 2. This is what they mean by the technical definition. We're going to primarily focus on order 1 and order 2, mostly because I can't help myself and I have a nice bunch of theorems, but we will actually delve into order k, autonomous and non-autonomous, but we're going to focus primarily on linear. We'll do some non-linear, but that's the one classification we haven't done, which we're going to do next video, is the difference between a linear difference equation and a non-linear one. So we have the order, we have linear versus non-linear, and we have autonomous versus non-autonomous, or homogeneous versus non-homogeneous. Therefore, our last remark is going to be, why can most books and why am I going to primarily focus on order 1? Let's do that. So to finish off, one more remark, remark 2, it's possible through substitution and introduction of new variables into the system. I'll do a couple of examples so you see what that's saying. Or we're going to increase the dimension of the state space, fancy terminology. Basically, we're going to introduce new variables into the difference equation. What is that going to do? Long story short, we can always turn a higher order. So if the orders 2 or larger and possibly non-autonomous, we can always turn that into a first order autonomous equation. Therefore, when we're studying general difference equations, if they're higher order and non-autonomous, we can do these clever substitutions, reduce it to a first order autonomous equation and a bunch of systems of them, study how to do first order systems of autonomous equations, and we're in business, and then we can backtrack and solve the higher order ones from that scenario. So we're going to focus primarily on first and second order ones and what their explicit solutions look like. How do we do this game? The first one is the Fibonacci sequence. This is order 2. We just saw this one. the difference between t plus 1 and t minus 1 is 2. Therefore, how do I, if I want this to be first order, it already is homogeneous or autonomous because I have no terms with just t's in them, but it is second order. I want to write this as first order homogeneous. How do I do that? I have to get rid of this guy then. What we're going to do is cleverly write yt plus 1 equals xt, or by reshifting the index, that's going to say that yt is going to equal xt minus 1. What is that going to do for us? Cleverly, I can now rewrite the system as xt plus 1 equals xt plus yt, and yt plus 1 equals xt. You see what that's done? It's now given us a system of difference equations, but they're both first order. This one is t plus 1 and t. This is t plus 1 and t. So what that has done is transformed this equation by introducing a new variable y. We've now made this and transformed it into a first order difference equation. For the second one, now it's first order. We go from t to t minus 1, so the difference is 1. But we have a non-homogeneous term or a non-autonomous term. So how do we cleverly substitute to get rid of this? What we're going to do this time is we're going to introduce another variable. Yt is going to be yt minus 1 plus 1, and then we're going to let y0 equal 1. If you meditate on that and calculate a few of them, if I'm going to y0 is 1, and if I calculate y1, that's going to be y0 plus 1, which will be 2. So what is that going to tell us? T minus 1 is equal to t. Therefore, you can see now the t can be put into a new system, and that's going to give me xt is equal to xt minus 1 plus yt minus 1. And now that is first order. There's another variable introduced, but it's first order and homogeneous, not non-homogeneous. So in either scenario, these two should hopefully help you convince that if we have higher order, we can turn it into first order homogeneous, and if we have non-homogeneous, we can still turn it into first order and homogeneous. Even if we have second order and non-homogeneous, there are still clever ways to combine these techniques to give us always a first order homogeneous equation. Therefore, in the next video, what we're going to do is spend a lot of time trying to solve first order homogeneous recurrence relations. Please subscribe right here and hit the notification bell. See you next time.